Welcome back, AP Statistics. This is the third and final installment of Chapter 13. We're going to start by talking about the probability of at least one or at least once. So we can use the complement of an event. What is the complement of an event? Well, if we have an event, say E, the complement of that event E is that event E not happening. So we could talk about the probability of E, the probability the event happens, or we can talk about the probability of the complement of E, which is the probability that E does not happen. So we can use the complement of the event not happening, to make computing probability significantly easier when we're using multiplication rules as well. So before, we saw sometimes that we want to refer to the complement of an event and not an event. We want to know the odds of an event not happening. But there's a sneaky way that we can use this when trying to find the probability of at least one or at least once. Rule number 6. Probability of at least one or once is 1 minus the probability of none or never. All right, so the odds of something happening at least once, if there are many times that this event could happen within one trial, that's a lot of computation, all right? But there's only one way that the event could never happen. So the probability of an event is 1 minus the probability of its complement. The complement of something happening at least once is it never happens. So this is a sneaky way in which we can use the complement of an event to find probabilities involving at least one or at least once. So for example, if I wanted to find the probability of getting at least 1 plus I, if you're not in my class, you have no idea what I'm referring to, this is called imaginary extra credit. I don't give actual extra credit. I've become low-key noteworthy for that, but I do give imaginary extra credit to my students. It doesn't register in their grade books, but they know they've done something good if they get imaginary extra credit. So if I wanted to find the probability of getting at least 1 plus I in this class, that would be equivalent to 1 minus the probability of never getting a plus I. So one of these two things is going to happen. You're going to get at least 1 plus I, or you're not going to get a plus I at all. Okay? One or the other needs to happen. So if I want to find the probability of getting at least 1 plus I can say 1 minus the probability that I don't, and that's the probability that I do. This is much easier than finding the probability of getting exactly 1 plus I, or exactly 2 plus I's, or exactly 3 plus I's, or so on and so forth. For each one of those ors that we could consider, we need to use addition rules of probability. So this sum could get really, really big. And I don't want to deal with that. So now we're going to apply our knowledge on using the complement of the event to address the at least one or at least once situations. We've determined that the probability that we encounter a green light at the corner of College and Main is 35%, a yellow light is 4%, and a red light is 61%. Let's think about your morning commute in the week ahead. And by the way, by week, the textbook means a 5-day work week. So we need to know that going in, or else this question gets really awkward. What's the probability you'll need to stop at least once during the week? Think about how you could use the complement of the event at least once to solve this problem. Give it a go and compare your answer with mine. Okay, I'll assume we're ready to continue. Let's check our answer. The probability of stopping at least once equals 1 minus the probability we never need to stop. So if we never need to stop, that means on Monday and Tuesday and Wednesday and Thursday and Friday, we don't stop. And all those ands involve multiplication rules of probability. And the odds of us stopping on one day don't change depending on whether or not we had to stop in a prior day. So all of those events are independent. So we can simply write this as 1 minus 0.39 to the 5th power. All right, that's 0.39 multiplied by itself 5 times over, and you would subtract that from 1. Okay, and so your answer would be about 99%, a little over 99% chance that you are stopping at least once, because never stopping over the course of those 5 days is very, very unlikely. Let's finish up this lesson with a couple of practice problems. Opinion polling organizations contact their respondents by telephone. Random telephone numbers are generated and interviewers try to contact those households. In the 1990s, this method could reach about 69% of U.S. households. According to Pew Research Center, Pew Research is one of the few organizations that is the gold standard for research. The other is Gallup. So Pew Research or Gallup, that is basically the gold standard for research of this kind. So Pew Research Center for the People and the Press by 2003, according to them, the contact rate had risen to 76%. We can reasonably assume each household's response to be independent of the others. What is the probability that, and we see letter A, the interviewer successfully contacts the next household on her list. And we'll be assuming the new updated proportion of 76% if you consider 2003 to be new. So we'll go with 76% there. Next, we're going to answer what are the odds the interviewer successfully contacts both of the next two households on her list? And we'll assume those contacts are independent events. The interviewer's first successful contact is the third household on the list. And then finally, the interviewer makes at least one successful contact among the next 5 households on the list. Give each of these a go, pause the video, and unpause the video when you're ready to check your answers. Okay, I'll assume we're ready to continue. Let's begin. Let's look at letter A. The interviewer successfully contacts the next household on the list. The probability of success would be 0.76, all right? That's just this number right here. Nothing too complicated there. Let's look at part B, successfully contacting both of the next 2 households on the list. Now, contacting one person has no effect on the next person you'll contact. So those are independent events using multiplication rules. Probability of 2 successes would be 0.76 squared, or 0.76 times 0.76, which would be about 58%. Let's look at letter C. The interviewer's first successful contact is the third household on the list. This one's a little trickier. If the first successful contact is the third household on the list, then you need 2 failures followed by a success. If the odds of success is 76%, the odds of failure would be 1 minus 76%, which is 24%. So 2 failures followed by a success would be 24% squared times 0.76, which is about 4.5%. Not a very likely event. And part D, the interviewer makes at least one successful contact among the next 5 households on the list. We see those words at least one. At least one. That means we're going to use the complement. The complement of at least one successful contact is no successful contacts in our 5 calls. So we would say probability of at least one success is equal to 1 minus the probability of no successes. And if we're doing 5 calls, we would have to fail 24% odds of failure 5 times over. 1 minus that number is basically we are guaranteed at least one success. And now we're going to talk about M&Ms, because why not? The 5 rules we've seen can be used in a number of different combinations to answer a surprising number of questions, says our textbook. Let's try one to see how we might go about it. M&Ms, milk chocolate candies, now come in 7 colors as of 2018. But they've changed over time. In 1995, Americans voted to change tan M&Ms, which had replaced violet in 1949. These are old I didn't realize they were that old. To blue. In 2002, Mars, trademark, the parent company of M&Ms, registered trademark, used the internet to solicit global opinion for the 7th color. To decide which color to add, Mars surveyed kids in nearly every country of the world and asked them to vote among purple, pink, and teal. The global winner was purple. Cool. In the US, 42% of those who voted said purple, 37% said teal, and only 19% said pink. But in Japan, the percentages were 38% pink, 36% teal, and only 16% purple. And interestingly, these percentages do not add to 100%. They actually only add to 90%. We need to keep that in mind. Let's use Japan's percentages to ask some questions. What is the probability that a Japanese M&M survey respondent selected at random preferred either pink or teal? Okay, so that's an or statement. So we need to use addition rules there. Number 2, if we pick 2 respondents at random, what's the probability that they both prefer purple? And number 3, if we pick 3 respondents at random, what's the probability that at least one, there's that phrase again, at least one, preferred purple? Take a moment, try each of these problems using a bit of addition and a bit of multiplication rules, assuming that each of these events are independent, and unpause the video when you want to check your answers. Okay, I'll assume we're ready to continue. Here come the answers. Let's look at number 1. The odds that a Japanese M&M survey respondent said either pink or teal. The probability of pink or teal, which is going to be 0.38 plus 0.36. We're assuming that these are disjoint events. We can't pick pink and teal at the same time, and that would add to 74% probability. Number 2, if we pick 2 respondents at random, what's the probability that they both preferred purple? All right, so we need a probability of purple, and I ran out of space over here, so I got to move down here. Probability of purple and purple would be 16% times 16%, which is a little north of 2.5%. And finally, if we pick 3 respondents at random, the probability at least one prefers purple is 1 minus the probability that none want purple. And the probability of none wanting purple, which would be the probability of not purple, well, if 16% of people prefer purple, that means 84% of people chose something other than purple, whether pink or teal, or since these probabilities add to 90%, I guess 10% of people just didn't care. So the odds of not choosing purple is 84%. We would cube that because we are picking 3 respondents. And 1 minus 0.84 cubed is going to be about 40.5%, a little bit north of 40.5%. And the odds that you have homework is 100%. Have a great day.